Hello student. In previous lecture, I have derived the step response of a second order system for different values of zeta. Okay. So see, this is the characteristics of step response of a second order system for different values of zeta. Okay. So in x-axis is our time and y-axis is our output. Okay. So see, for different values of zeta, our step response vary like this, or our step response behave in this manner. Okay, for different values of zeta. Okay. Now see, the underdamped second order system is a common model for many second order systems. Okay, so therefore in this lecture I will discuss the transient response characteristics of a second order underdamped system for a unit step input. Okay, so in this section our objective is to define transient response specification of a second order underdamped system. Okay, so see, this is the underdamped response of a second order system. Okay, so see, from this figure we can observe that the step response has a number of overshoots and undershoots before reaching steady state, and this overshoot and undershoot decay exponentially. Okay, now see the characteristics. Here our x-axis is our time and y-axis is our output. Okay, and here I have given TR, TP, TS. So here TR represent rise time, TP represent peak time, and TS represent settling time. And here is their MP. So MP represent peak overshoot. Okay, so these all are time domain specification or transient response specification of a second order underdamped system. Okay, now I will discuss this term. Okay, so first is our rise time. So see, what is rise time? The rise time is the time required for the system to reach 90% of its final value first time from the initial value of 10%. Okay, so what is rise time? So rise time is the time required for the system to reach 90% of its final value first time from the initial value of 10%. Okay, next is our peak time. So what is peak time? The peak time is the time required for the response to reach the peak of the first overshoot. Okay, so this is our first overshoot. This is our first overshoot. Okay, so peak time is the time required for the response to reach the peak of the first overshoot. So this is our this is our peak time. Okay, this is our peak time. Okay, now next is maximum overshoot. Maximum overshoot is a measure of how much the response exceeds the final value following a step change. The percentage of maximum overshoot can be calculated as like this. So the percentage of maximum overshoot is equal to first peak value minus final value divided by final value into 100%. Okay, so first peak values represent CTP minus final values represent C infinity divided by C infinity into 100%. Okay, so this is our maximum overshoot. Okay, and maximum overshoot is represented by MP. Now settling time. So what is settling time? The settling time is the time required for the response to reach and stay within a specified tolerance band of its final value. So the tolerance band is usually 2% to 5%. Okay, so this is our settling time. Now decay ratio. So see, what is decay ratio? The decay ratio is defined as the ratio of the amplitude of first two successive peaks about steady state value. Note that the response shown in this figure has the first overshoot of amplitude is A, capital A. Okay, here I have mentioned where is A, and second overshoot of amplitude is capital B. Okay, so this is our A and this is our B. Okay, so therefore decay ratio is capital B by capital A. Okay, so here I have given the definition of our time domain specification. Okay, so rise time, peak time, maximum overshoot, settling time, decay ratio. Here I have given the definition. Okay, now we will in this slide we will derive the rise time. Okay, or how we calculate the rise time. We will calculate the rise time. Okay, so see. Consider a unit step response of a second order underdamped system. Okay, and we know the unit step response of a second order underdamped system is this Ct equal to 1 minus e to the power minus zeta omega and t divided by root under 1 minus zeta square into sine omega dt plus phi. Okay, where phi is our tan inverse root under 1 minus zeta square divided by zeta. Okay, so see, let us assume that Tr is the time required for the system to reach 100% for the first time. Okay, now that's why Ctr equal to 1, because Tr is the time required for the system to reach 100% for the first time. That's why Ctr equal to 1. Okay, since our final value is equal to 1. Okay, but we know Ctr equal to 1 minus e to the power minus zeta omega and Tr divided by root under 1 minus zeta square sine omega d Tr plus phi. Okay, now here put the value of Ctr. Okay, so if we put the value Ctr 1 in this equation, okay, then 1 cancel, that therefore we get e to the power minus zeta omega and Tr divided by root under 1 minus zeta square into sine omega d Tr plus phi. This is equal to 0. Okay, now from this equation we can write sine omega d Tr plus phi equal to 0, because e to the power minus zeta omega and Tr divided by root under 1 minus zeta square not equal to 0. Okay, so from this equation we can write omega d Tr plus phi equal to n pi. Okay, so for first peak n equal to 1, therefore our rise time Tr equal to pi minus phi divided by omega d. Okay, now we put the value of omega d in this Tr equation. So our final equation is Tr equal to pi minus phi divided by omega and root under 1 minus zeta square. So this is our rise time equation. Okay, now we will derive the peak time. Okay, so we know the peak time Tp is found by differentiating Ct and letting this derivative is equal to 0. Okay, so differentiating this Ct means we differentiate this Ct. Okay, so see, So see, after differentiating, differentiating CT with respect to T, and this differentiation, putting this differentiation equal to 0, we get this equation. Okay, so see, exponential term is not equal to 0 at t equal to Tp. That's why we can write zeta sine omega d Tp plus phi minus root under 1 minus zeta square cos omega d Tp plus phi equal to 0. Okay, but we know zeta equal to cos phi and root under 1 minus zeta square equal to sin phi. Okay, so see the expression. So see, now the expression will be sin omega d Tp plus phi cos phi minus cos omega d Tp plus phi into sin phi equal to 0. So here we put the value of zeta and root under 1 minus zeta square. Okay, so after putting the value of this, we get this equation. Okay, now see, from this equation we can write sin omega d Tp plus phi minus phi equal to 0. So from after simplifying this equation, we get omega d Tp equal to 0, pi, 0, comma pi, comma 2 pi, comma 3 pi. Okay, so since the peak time correspond to first peak overshoot, so we have omega d Tp equal to pi. Okay, so therefore Tp equal to pi by omega d. Now we put the value of omega d. Omega d is nothing but omega n root under 1 minus zeta square. So our peak time Tp is equivalent to pi divided by omega n root under 1 minus zeta square. So this is our peak time. Okay. Okay, thank you. Now in next lecture, I will derive the maximum peak overshoot equation and settling time equation. Okay, thank you, student.